Okay, I think we're just about ready to start. Um, Hello, everyone, and welcome to today's IFHE webinar. My name is Yoshihisa Hirayama, and I will be your host for today's session. My background is in HVAC systems, and my professional focus is on healthy indoor climates and occupant health. I've been actively involved with the Healthcare Engineering Association of Japan, HEAJ, since 2013 and serve on the executive committee of the International Federation of Healthcare Engineering, IFHE. Now, IFHE brings together healthcare engineers and professionals from around the world to share knowledge, advance best practices, and support better healthcare environments globally. Um, Today's IFHE webinar is proudly sponsored by Mazzetti of US, an employee-owned engineering firm known for its long-standing work in healthcare, sustainability, and integrated building design. We sincerely thank Mazzetti for the support of today's program. So, before we begin, I would like to note that this Zoom webinar offers closed captioning and live subtitle translation into multiple languages. You can enable this feature using the caption or translation options at the bottom of your Zoom screen. I'm not exactly sure how many, there is different languages, different regions, countries we have here participating. Just to put a little comment in Japanese from my side, こちら本日すべての何ですか字幕の言葉を選んで字幕を自動翻訳で設定することができますので、下の詳細のボタンをクリックしていただいて、字幕表示というところをクリックされると、日本語の設定とか、できると思いますので、もし日本のから、参加されている方、ぜひお使いください。So, we also encourage you to submit your questions at any time using the Q&A feature shown here below. And we will address as many questions as possible during the discussion period at the end of the presentation. So now it's my pleasure to introduce today's speaker. We are joined by Jonathan Hernandez, Director of Geoscience at Brightcore Energy. Jonathan has been working in geothermal energy development since 2010 and brings extensive experience across the Americas, Southeast Asia, and East Africa. So today, Jonathan will share insights on how geothermal heating and cooling systems can help future-proof hospitals, covering how these systems work, real-world case studies, and the funding strategies and incentives available to support the adoption. So with that, please join me in welcoming Jonathan Hernandez.
Thank you very much, Yoshi. I appreciate the intro. Hello, everyone. Good morning, good evening, or good afternoon, wherever you may be. My name is Jonathan Hernandez, and just to test the Spanish, muy buenas tardes. Es Jonathan Hernández aquí de parte de Brightcore Energy para ustedes a presentar un poco sobre la energía geotérmica. Essentially saying that this is a class for geothermal energy, so I hope it was well translated. As Yoshi alluded to, this is for the ability to use geothermal or ground source geothermal for future proofing critical assets such as hospitals and healthcare buildings. Just making sure everybody can see. Are we good to go? I'm going to assume everything's great. All right, so a little bit about Brightcore and why I'm here and why we're here to tell you about geothermal energy. Brightcore is based out of New York here in the United States, where I am located currently. We also have an office in Stockholm, Sweden, where we have our Center of Excellence. And it began as actually a commercial and community solar business that then developed into advanced energy efficiency with lighting solutions. And over the last 4 to 5 years, because of specific policies in the United States, such as the Inflation Reduction Act, the CapEx incentives for the installation of these systems are now making them far more competitive as an electrification option. Now, you're basically talking about what solar went through 15, 25 years ago, where the federal subsidies allowed it to compete, even though it was an intermittent solution. Now we're talking about a base load decarbonized electrical solution to heating. And with that, geothermal has now become the largest division in the company. I began at Brightcore at about employee 60 something, and we are now at well over 120. So I will also say there was a version of this presentation earlier, and so that's why it says May 13th. But happy Thursday to everyone here joining us May 14th on your side of the globe. Brightcore, in terms of developing geothermal projects, actually runs the gamut. And what I mean by that is geothermal systems are a construction. They are part of an increasingly long-term view of infrastructure that would require the same type of rigor and analysis that a construction project would entail, such as master planning, feasibility studies, then going into heavy equipment, trades, health, safety, stakeholder engagement, noise, spoils, all these other aspects of actual on-site operations. And then, and this is a lot of times what had happened in previous generations, and I'll go over that, is the handoff to the facilities managers, to the people who actually have to run the system. Now, technology has gotten to the point now where there's all automated systems, passive or active, meaning it can either whistle and set off the alarm, or it can notify you and solve it for you as an active, let's say a valve or a pump or something. So these BMS systems now can integrate geothermal systems. So as it always chases an optimal flow state for transferring energy or load sharing, demand response cooling, heating, there is another set of digital eyes that is allowing the system to function at an optimal rate. So that is how the delivery of the systems go from conceptual through to long-term, essentially base load, cyclical energy solutions. When we're talking about the implementation administratively instead of operationally, we're looking at a classic design, build, operate model. What we've seen in the past, at least here in the United States and in other parts of the world, you're going to have a fractured market in terms of delivery of the services that are required. Energy modelers will likely stay within the MEP realm, and a lot of times if it's a retrofit, there's an MEP of preference, all the way into construction managers, general contractors, trades. Again, it depends on the site, and we'll talk about the subsurface as how it depends on the site. But for example, a retrofit, the geothermal system, I don't mean to be glib, but is the star of the show. In a new construction or a new build, geothermal is a line item of a much larger project. So it depends on the phase and on the actual parameters as to how the geothermal system would be approached in developing, procuring, and maintaining and owning, and really who owns each responsibility in those phases. So anything from turnkey to subcontractors, Brightcore can do both, but that's typically what the industry has created in terms of installing these systems. A little bit about myself as to why I'm here, and Yoshi so thoughtfully provided some words as well. My background, yes, has kind of been international, but one of the things is you'll see at the top two images, proudly, they are not AI. Those are me on a phone. The top left in those images is Papua New Guinea at an open pit gold mine on an active volcano where geothermal power generation was hosting all of the megawatts of electricity needed, 35 megawatts, through hydrothermal for an open pit operation on an otherwise uninhabited island. On the far right, at the top, are the Andes Mountains, and those are hot springs. And same thermal anomalies, very different latitudes, elevations, and longitudes, and that's in Chile. And at the bottom is in New York. So geothermal in so many places. Now the top two are power generation and the thermal anomalies in a different beast altogether, and I'll explain how. But I did want to make the point that I've been able to see what works in both and try to bring that and impart that to this course so that you're well-rounded when it comes to geothermal. It's new in a way, but I know we are currently getting our flowers, as they say. So 100 years to become the overnight sensation of geothermal. So let's get started. This is a sophisticated audience, so I'd like to begin with more mid-level concepts in order to get the ball rolling. So we will start at the beginning. What better place to start than what I mentioned earlier? Power gen versus what we're going to call heat exchange. So on the left is, if there's any Kiwis in New Zealand, very, very familiar, Indonesia, the Philippines, Japan as well, has geothermal power generation due to the Pacific Rim and volcanic anomalies creating a higher than normal, what we call thermal gradient, right? Degrees Celsius per kilometer is down. And in those locations, typically in these regimes, you will have a fractured system, a permeable matrix that will allow a working fluid to capture heat as it's transferred from hot rock, from decaying radioactive rock in the mantle and into a place we call the moho, the ductile layer, and even higher into, let's say, a fault, which the faults are used rather as an aperture network to advance upwards and depressurize. At the end of the day, essentially, you have what's called a production well and an injection well. And there's some housekeeping later in terms of the vocabulary we use, but what you'll see is two very distinct things. A production well creates and brings the heat into the building to be used. The heat is then used and interacts with another liquid in order to create the power generation, isopentane, isobutane, but it's called an organic Rankine cycle. It's a binary approach, very similar to a heat pump. And then the enthalpy is released into that system, and what remains is the same working fluid on a much lower energy state, injectable water, ideally. And that is re-injected into that same aquifer to then re-pick up the heat, and the cycle continues. That is power gen. That has been understood since the late 19th century. Now we go into heat exchange. Heat exchange has had a few makeovers, but in the latest version of it, it is a closed loop of high density polyethylene that uses a working fluid similar to water in this case, but that's an open loop in power gen, that will then transfer heat from or to the bedrock. And we'll get into that later on. The depths are fairly different. The order of magnitude of investment is extremely different. In deep drilling, we're talking 5,000, and you may have heard of EGS, companies like Fervo that I believe went public today at the NASDAQ, FRVO. We're looking over there at oil and gas depths of 20,000 feet. In geo exchange, what you would have at your medical facility within your tax lot would be somewhere between 500 to 1,500 feet. The kind of things that are much easier, much more tame, less harsh, and faster to install. So heat exchange has taken place in very similar strides as power generation. So on the far left, let's call that generation 0, is an open loop. There's similar aquifers to be tapped, to be pumped, to be brought to the surface and then re-injected. There you have your production and injection wells. So you have multiple drilling operations, and you're beholden to A, the permeability of the rock, B, the water and fluid conditions that may affect your pump, electric submersible pumps within the wellbore, as well as permitting of drilling something that interacts likely with potable aquifers because of the depths. Fast forward to one drilling operation of a concentric single column well. What this does is it turns this drilling one well into both a production and an injector, using the annular space as the injector from the building. You see the red arrows from building. And then the blue electric submersible pump within the inner diameter column to recover that fluid, that water that has been exposed to the rock and either releases or exchanges heat by recovering it. That, again, is a pump, maintenance, permitting, but also here, and something I didn't mention in the first one, you are beholden to a very precocious water table. Now, the example I made earlier is in an underdeveloped area, and you have a really good notion of the kind of water table depths you deal with seasonally, over a full year, you'll be in good shape. However, as development happens around you, meaning new buildings, new equipment, new neighbors, that water table over time will deplete. What that does is twofold. Number one, changes the water quality. Number two, reduces hydrostatic head on that pump, making your pump work harder. Therefore, your losing efficiency and paying more electricity for a less efficient product. So as you can imagine, over time, single column wells weren't very popular. So the permitting of the open loop, no longer feasible in today's environment, and standing column wells, an outdated technology that has too high of an O&M and too risky and dependent on subsurface conditions. Fast forward to the closed loop solution that we will talk about in detail today. Closed loop means circuits of boreholes that have a high density polyethylene pipe, flexible, that will go down into each borehole, designed in circuits to interact via a manifold with a heat pump, water to water, water to air. It can be hybridized with an air source, meaning heat recovery chiller, 6-pipe system. There's several ways to make it work. But the point is, you're no longer depending on aquifers, you are no longer permitting for wells, and you are no longer requiring pumps that are exposed to the elements in the subsurface. De-risk, de-risk, de-risk. Read OpEx, OpEx, OpEx. What we're looking at here is the best way I can describe how base load constant temperature is leveraged in the peak seasons. The reason for that is, on the left, it's not intuitive to say the words geothermal cooling, but that's exactly what's happening. 85 degrees is I'm from Los Angeles. That's fairly mild for a hot, quote unquote, summer day. I know some of us may be joining from Australia and may giggle at an 85 Fahrenheit, or let's call it 25 centigrade, 22 centigrade type day. But the ground temperature will remain that 17 or 55 F temperature consistently. So now you have a delta T in your favor as a heat sink. And as we know, the ground in most problems is an infinite 2D barrier that will always have enough capacity to dissipate enough heat. Now, there are certain thermodynamic limitations, and we'll actually get into some of that detail. But overall, a properly designed system will allow you to, not lose that energy off of the roof and rooftop units, for example, but make it an asset for a later, colder, quote, rainy day. If you have hard bedrock, meaning high density rock, obviously it can be at surface. If you're lucky, it can be below significant overburden. But either way, it's actually not something to be avoided, but something to be exploited. And what I mean by that is thermal energy storage, and we'll get a little bit into that, but you can actually increase that ground temperature on average. And when the winter comes, you're, let's say, now at a ground temperature of 70 degrees F, and the air temperature is still below freezing at 25 Fahrenheit. You cannot rely on an air source heat pump to produce heat during a blizzard efficiently. That pump is going to work a lot harder, and you're going to not see the savings that you were promised, as with the standing column well. So when you have a ground temperature that is consistent and or pre-charged, your coefficients of performance, your efficiencies, shoot up during the peak seasons. This is when geothermal truly is the star of the show. What about when it's 55 outside, Jonathan? Great question. Delta T is 0. Next question. No, I'm kidding. No, what happens in these shoulder seasons, you may have heard me earlier, I mentioned hybridizing. Well, that's when you can actually offset, whether it's off-peak hours, and you can run certain using air source to cool down, but instead of using it off the roof, go through a heat recovery chiller and bring it back down into the bore field, for example. So you can use both in tandem, and it can still have a place to be used. Or it can be maintained as your full baseload and then use the air source during the peaks as well to help offset. So several ways to work it, but cooling and heating on a sinusoidal 8760, 8,760 hours in a year, you want to see a balance. You can play with the peaks and the troughs so long as December 31st and the next January 1st keep lining up year over year. You will have a baseload reliable system, and you can play with it, and that's what the modeling is about. But overall, you're using this. You're exploiting thermal conductivity through a solid, essentially heat transfer through a solid, using conduction. And that's what the high-density polyethylene pipes are, loops set within thermally enhanced grout. Now, you'll notice that thermal conductivity is an efficiency rate. It doesn't measure the actual capacity of the system. It just tells you how fast heat can be transferred in and out of that particular borehole. That will be a factor in determining how many boreholes, how deep, the kind of drilling strategy that's required. It'll affect your budget, the permitting, the scheduling, and even loop selections. There's more than one type of loop. There are high performance exchangers that can get you 10 tons, 12,000 BTUs per ton, or regular loops that can get you, let's say, 3 to 5 tons per hole. It all depends on the conductivity and on the well design, which is based on that conductivity. Capacity is the sticker price. So you may want to know what type of engine you have, but how fast can it go? Here you have your actual capacity of the system, which is directly proportional to the rate. There you see the heat transfer rate. It's BTU per hour per foot. And this is done through what's called a thermal response test. So typically you drill a test hole, ideally, and happens 99% of the time. Haven't been on a project where it hasn't. That hole is then used. It's not a sunken cost. You don't lose it. You will use it. But it provides your first true in situ data. Up until then, you're dependent on geologic information, GIS files, maps, maybe offset well data if you're lucky, oil and gas, water, mining, etc. But no one knows what's under your parking lot or under your basement until you actually drill it, which is one of the reasons we employ logging, whether if it's directional drilling, angled, inclined, we'll run gyros, but also to have the cuttings to know what type of rock we're dealing with. And that is why a thermal response test or a thermal conductivity test is performed to finalize your design or finalize your bore field. It won't make a huge difference. Typically, it just reconfirms what's already known. But in off chance, it just means wells may get 10 feet deeper. It doesn't affect materially your cost or your scheduling. I love this image for two reasons. Number one, it's pretty straightforward. But number two, on the right, that is a true geothermal system. So far, I've discussed drilling, I've discussed loops, I've discussed rock properties. What I haven't really discussed is where all of that gets connected into. Now here, the way the system is segmented is a green box below that shows all of the subsurface infrastructure through the borehole construction and the loops there within. On top, you have the blue box that shows the mechanical interior system that uses and leverages, and in fact, will be used to balance the bore field because we love balanced loads. And why I put that up there is one won't work without the other, but it's also how policy sees it. Here in the United States, we have what's called the Inflation Reduction Act, and that CapEx that I mentioned and that solar example, that solar analogy of having the subsidies bring down CapEx, well, it applies to Division 23 mechanicals, which means fan coil units, ductwork, even envelope efficiencies that are then tied directly to the loop that will be used. Those also will be eligible, and that really can help with you phase out your planning and really maximize the incentives, but also makes it cash flow positive when compared to the other alternative of electrification, which is air source heat pumps, because they do not have access to these incentives. So if you're going to go electrical anyway, that bore field plus the mechanical incentives then really make a big dent in the initial CapEx required. On the left, you'll see the types of U-tubes, gives you a better idea. There's a socket bend, there's a unicoil, there's concentric, those are high performing. But also I want you to notice that it will be grouted backfill, but those are older types. This will be grouted from the bottom all the way to the top. A lot of times within the overburden or the unconsolidated substrata, you will have to run casing, steel casing, K55, either 8-inch, 6-inch nominal casing, with a casing shoe that with the rig will actually drive the casing into the bedrock. The reason this is done is to protect in the areas that will either be beholden to unconsolidated, and you don't want any type of lateral stress on your column if it's just a column of grout. You want that to be held in. Once you're in hard bedrock, it's a completely different regime of stress that's required to make any dent in the column. But in the unconsolidated, right, that's the big difference. That's why. And in some places they don't grout. Some places they leave it within the aquifer. closed loop pipe. But in Scandinavia, for example, they leave it in the aquifer just for whatever reason. They have to have it as a sink, and water is a great way to wash away thermal energy. And that's just to show one in and out, blue, red, one borehole within that box being represented. These designs don't land on their own. They're part of a much bigger design document, for example. So geothermal goes under the same rigor of any other MEP line item. Here, what I'm showing is in the blue box, bottom right, the borehole. On the top left are circuits. It's not one large loop that comes out of one end of the pump, goes through 100 boreholes, and comes back into the pump on the other end. It's designed via a manifold that you see in the green box, and the circuits there are 6, 8, 10, 12 boreholes long. The reason for that is either A, you need circuits for both heating and cooling simultaneously, especially if you're going to be doing load management, load sharing among other users, such as a thermal energy network. But also, it provides that redundancy. Losing one borehole would provide that Christmas light issue. You lose one borehole, you lose that whole ambient loop. There are ambient loops. It's a different type of design. It's much larger pipe. It's a different type of purpose. That's not what these are, if you may have heard of those. These are circuits in a bore field. And so think of them as spokes on a bicycle wheel. Some may be used for cooling, some may be used for heating, but they all end up talking to the manifold in the vault or in the mechanical room. Classic heat pump, again, this audience, these are very basic, but just it works in cooling and heating cycles, as I showed you earlier in the geothermal cooling and geothermal heating. In the ambient, this is what's happening in the mechanical room. But really, it's just to show that we can plug into retrofits and use these systems as redundancy. So you may not be at end of life and are contemplating a geothermal system because there's an incentive. Well, the end of life may be 10, 5 years away. That's still your redundancy, and it actually end of life gets extended when you're not using it. Am I right? So all of a sudden, your bore field can be still installed with incentives, but you will still have that requirement of redundancy. St. Patrick's Cathedral here in New York City was drilled and installed by the Senior Vice President of Engineering here at Brightcore Energy. And it uses geothermal boreholes to run the entire cathedral. By law, it has a redundancy of a gas boiler. They have not used that for several presidential terms, is what I was told. So you consider how that would stack up in terms of extending your use, whether it's an electric boiler or you just are transitioning from gas or fossil fuels, diesel oil, etc. But that's really the point of that slide, that it can be seamlessly integrated even if it's not the only thing in your arsenal for solving your HVAC issues, which are many at these healthcare facilities. COP was mentioned earlier, the coefficient of performance. One of the things I've always loved about following a scientific path is finding these cool things that make it fun for me. Energy, as you can see, bet my career on it, and many of us here did, is interesting that a car stereo, a nuclear power plant, and electricity running through the national grid are all measuring the same thing in different ways, but watts. So when we're talking apples to apples, way to equate thermal energy and electrical energy and what comes in and what comes out, that's your coefficient of performance. So in this case, an air source heat pump system, 1 kilowatt of electricity in, 3 kilowatts, 2.5 kilowatts of thermal energy out, annual average load. That's great when you compare it to an electric boiler, which is either 1 or less. You look at an electrification system when you're decarbonizing and future-proofing, especially when you're trying to transition away from fossil fuels for geopolitical purposes or cost purposes, supply chain issues, etc. Geothermal gets you 4.5. Now that 4.5 is a published, very understood number. What I'm here to tell you is I've seen that thing shoot up to 6, 7, 8, given the right peak conditions. I've seen average values jump up to 5 or 5.5 even. Colorado Mesa University in the United States famously had theirs audited and an annual average close to 8, about 7.7 if I'm not mistaken. So I'd be happy to send that publication, but it's really impressive what you can do on large campuses with many loads, whether it's Heavy cooling, doing a lot of waste heat, and vice versa for domestic hot water, laboratories, sterilization, etc. You can really, really find the savings the more you use it. Some of the site recommendations and some of the discernments we do when we're looking at retrofits, for example. I mentioned end of life. The best would be going from heavy carbon or electric resistance because you're kind of familiar with having that electric base be your energy supply. But then also you look at boilers and water source heat pumps. We like water to water. It's great to communicate, makes our baseline readings on the energy model uh, easier. Cooling towers, we see that a lot. And in a place like healthcare facilities, recovery, we've seen that from many prospective clients on the out of sight, out of mind nature of the bore field and removing humming noises on the surface, on the roof, steam. Instead, they want to see more green areas, have more open spaces, have more walkable areas, things that geothermal can provide besides saving you money and besides providing higher efficiencies that we see, but it's also an architectural bonus. Here we have the geothermal project development chain. By the way, feel free to ask questions, and I'll rely on you, Yoshi. I don't know if there are any questions thus far. I'd be happy to answer any before moving on, because we're about to hit the end of this part, which is really how we look at existing buildings, but I'd be happy to go over anything so far.
Okay, thank you.
Yes.
Do we have any questions popping up? Lara, do we have any questions relevant to the let's say the first section of his presentation, or we can save the questions to the end?
Let's save.
Yeah, either or. Yeah. Oh, sorry. Go ahead.
No, let's save the questions till the end.
Will
Okay,
do.
great.
Great. When we look at this 8760 data, for example, what we're seeing here is the uses of the building. If you notice, warehouse and large office are going to act very differently. You see how the cooling actually balances out all of that heating. And that's really important for us on how we design. Now, types of circuitry, types of exchangers, you look at data centers, you look at warehouses that don't rely on human interaction, but healthcare centers are a little bit of both. I've seen laboratories, university hospitals with both very, very intense laboratory equipment and high loads all hours of all types of the year, as well as something that's perhaps far more that looks like, let's say, a typical office. Both can be modified and customized and hybridized in a way that is optimal. But we actually, in the geothermal field, really, really like health facilities for two main reasons. Number one, we know that these geothermal systems, I mentioned the out of sight, out of mind, but also think of Legionnaire's disease, think of filters and cleanings and inspections, think of that O&M that disappears because you're in a closed loop. These closed loops are meant to last 75 to 150 years with proper operation and maintenance. Um, you can build on top of these. The only time you wouldn't be able to is on a pressurized foundation slab. Uh, that's just more of a water pressure issue, and it probably could be solved with some drilling tech. But right now, that's the one time we try to avoid that. Everything else, if it's an open field and you want to build on top of the bore field, that's not an issue. The pipes come up and then they are 90 degrees bent over into trenches, usually 3 feet below grade, into the mechanical room, into the buried vault, etc. So that's really, really important in terms of retrofitting and for health facilities. When we look at facilities like health facilities, we know that it's going to be chock full of infrastructure. So we look at water tunnels, subways. This is in New York, but also the depth to bedrock for the reasons I mentioned. The number of feet of casing you're going to require. Can it be a thermal energy storage system, etc.? Is there an aquifer? Are there faults? What's known about the subsurface? That kind of stuff. But then putting it all together. Now that we've assessed it, we've done a feasibility, now we have to kind of determine where we are. When we're talking about the design, this is how the development usually goes through that pre-feasibility into a prospective bore field. It's agreed upon, design, build, then we go into drilling. These are the three most common rigs. The one on the far right is a truck-mounted water well rig. This is what has been keeping geothermal alive for the last 45 years in terms of geothermal heat exchange. Come off the shelf technology from the mining world, which is a lot what Brightcore uses, we now have faster, stronger, safer, and more compact designs that are allowing different bore fields that were never considered to really happen. An application of that on the bottom left is a mini rig. This is a Comacchio. It's an Italian mining company. In mines, much like in Papua New Guinea that you saw earlier, you have to be fast, you got to be compact, and you have to be accurate. That's exactly what we need in an urban environment or a campus environment. The smaller rig here that you see was hoisted down into the basement of a building, and we did about 20 boreholes, enough to provide the tonnage for all of the common areas of a 100-year-old building in New York City next to Central Park in the Upper West Side, which is high value, to say the least, real estate. What that meant was low vibrations, low noise, low disruption, which I'm sure is very key for health facilities as well. We mentioned the O&M at the beginning. This is an interactive dashboard, gives you an idea of how it lays out what the bore field is doing with respect to the BMS. Now that we've got a better idea on how these things are developed and how they're installed and what kind of structures are taking place, let's look specifically at drilling, and we're going to look at networks. So drilling, I mentioned we're going to do some housekeeping on some of the vocabulary. Well, I told you I'd mentioned well earlier. This is the only other time in the presentation where I will mention well, and that is well intended, pun totally intended. A well will interact. That's what we talked about. Boreholes do not. I mentioned casing, right? So now you have steel casing. Within, you have a column of grout, hardened grout, and within that, you have high-density polyethylene pipe. And all of that is isolating water plus a little bit of food-grade glycol. And only really in extreme conditions where tundra and permafrost may be an issue. That's the only reason. Other than that, it's distilled water. That is what you're isolating with the grout, with the casing from potable aquifers. So that is why a borehole has, over the last couple of years, just in New York, you'll see later, but depths were usually limited to 499 feet, not for any thermodynamic design reason whatsoever, but strictly for an administrative. Don't want to get to 500, it becomes a mining operation. 499, excavation. In Texas, drilling is regulated by the Railroad Commission. I mean, it just happens to be where you happen to be and what they are used to doing. Now we're seeing boreholes much more well understood, and for these main reasons. That's why closed loop is so important. And you're seeing closed loop in power generation as well. Reliability. How we make these holes really depends on what type of subsurface. The big takeaway here is that the first two drill bits, and some of you may not have ever seen a drill bit before. This is the same type of stuff, mining, oil and gas, water, and geothermal that we use. On the left is the tricone. This is to get through soft rock, unconsolidated. Polycrystalline diamond, yes, diamond, is to get through harder bedrock quicker. If you, for example, have the ability to incorporate what we call percussion drilling down the hole hammer tools, as you'll see on the far left, the action is happening downstairs with an actuated piston. All other drilling force is produced by the rig itself. These hammers use air or water. Air is pretty preferred just because air is free and you don't have to truck it to site. But also, this type of percussion drilling is really good in hard rock and is used in mining very successfully. There is water hammer, though. And water hammer is what would likely be used in health facilities because of the low noise. You don't have to compress air to come down 500 feet and back up 500 feet hard enough and fast enough to push rock out of it. That's a lot of compression of air. The water hammer does not have that, dampens the effects of any of the spoils coming out, low vibration because you're not pushing from the top, you're simply actuating a piston down below. So all of these things allows that type of drilling to take place. No earplugs, no crickets, right, for biogenic gas or of any kind, and no eye guards, nothing. And in fact, they're drilling with the remote control on the desk. So, or I'm sorry, in the gentleman's lap on the left. So there you go. This is, and in the basement of a building. So this is the type of technology now that is available. So you may have seen those water well trucks, and those are still used. That has its place, but the type of drilling, where we can drill and how we drill, has made a big, big leap in the last 5 to 10 years. How we drill can be part of the design. Here we have 850-foot true vertical depth, 850-foot boreholes spaced at 21 feet. This is what you're shown on the right. This would take about 60,000 square feet. That's a lot. That's a huge parking lot, a big green area, something. Not everybody has 60,000 square feet, but I guarantee you the tonnages and the loads required at health facilities, 138 boreholes, it'll make a dent. May not be everything, but it'll make a dent. Now, there's other designs that we can do. And one of those is on limited spacing. Angled or incline drilling can reduce the surface footprint disruption while still taking advantage of what's called the thermal mass below. When you're looking at these angles, you're looking at 5 degrees, 10 degrees, or 15 from the surface. It's a little more accentuated here in some of these graphs, but what you'll notice is you'll stay typically within a pretty narrow footprint. And then the deeper you go, well beyond subsurface infrastructure, water tunnels, etc., is when it begins to flare out. That flaring out and that residence within the rock on its own, isolated from other boreholes, counteracts the intermingling that takes place as they're all spaced together at the top. So if you're wondering about thermal interference, in all of our 30-year stochastic models, we do Monte Carlo simulations, but we also do what's called free placement, which is a 3D grid, cell of heat flow in various matrices. What it's shown is that it's negligible over time if you have the proper spacing. And if you'll notice, some are blue, some are red. We talked about circuits. That's the kind of designs that are doable now. And I say now because this is a true story. An Ivy League school in Connecticut put out an idea to do a pilot project, and they wanted to see what can be done on this bike path. Now, this bike path, as you can see, is in a very developed area. You look at everything that's already there, you would probably not look doing much beyond vertical boreholes spaced out, etc., as we looked at earlier. Or if you have the incline and a little inclination, pun intended, you can do a far more complex design that can create a rugby field out of a bike path. Obviously, the rugby field is 850 feet below depth, but nonetheless, you have that thermal mass now that you're accessing for heating and cooling off just disrupting a bike path on a busy campus. I'm sure health facilities can relate. Again, types of drilling, just recapping here, conventional versus this limited access rig. Here's some of the specs and some of the numbers that you're dealing with in size. Inclined also is going to need some overhang space. So when we're looking at these larger rigs to do these inclined drilling, sometimes it's better to use the smaller limited access rigs that can also do incline drilling. All right. Where we've actually applied this in the last 24 months is pretty awesome. And I'll start with one of our crown jewels. Well, that same university was so happy with that bike path pilot idea that it actually opened up everyone's thoughts on the project and said, actually, look, we were playing around with the idea, but this is what's happening. We're creating brand new buildings in blue in the outline. This red line is the very edge of our campus. And we know that we have all of this infrastructure at about 3, maybe even 10 feet below grade in certain areas. And if we give you this area to drill, what can you do? And it was almost like a reality show. There was more than one bidder. It was an open process, and it was maximize the load, minimize the disruption. What can you do? And that's what we did at Brightcore. And we decided to apply everything I just mentioned for you. Going deeper with different drilling tools, drilling rigs, designability, all of these things, and understanding how many buildings and what type of buildings that were going to be designed to create a bore field and then the bore field design of both verticals and inclined boreholes. Now, if you notice, we really maximized both to the tax lot line. Literally, that's where they end. Those circles are circles of cones of confidence, really. Also to show spacing at depth. But this has turned into a 260 borehole project providing over 4 megawatts thermal to 12 buildings at Yale University in New Haven, Connecticut. And we're just wrapping up the drilling. We compressed the drilling to what would have typically taken about 18 months to about 8 months. And we've done that through multiple rigs and working with Turner Construction and other large project managers and management to the point now where it's got 3 buried vaults. So 3 systems talking to each other, serving multiple buildings. That is a thermal energy network. And in my opinion, humbly, little bias, will be the probably most advanced thermal energy network in North America. So that is one case study, and this is what the model now looks like in 3D to kind of give you an idea. And as a fun challenge, you can kind of see where that original bike path. So here is this area that will, these are the blue buildings that will be served, and this blue polygon is where this bore field resides. And this whole area is actually a green space in the future. So it doesn't have to be, it can be, but it doesn't have to be built upon. It can just be left there for beautiful green space. And that's what they did at Yale. Java Street is a mixed-use building in Brooklyn. I like bringing this up because this used to be a brownfield on the coast of New York, right where all the naval shipyards were. And it is the largest bore field in the history of the state of New York. 320 boreholes, 499 feet for the reasons I mentioned earlier. But it's 100% geothermal, heating, cooling, and I believe domestic hot water as well. It's a passive house envelope, so it's extremely efficient. And it has really brought to the attention of the city and to the developers in the area. They're keeping a close eye on it, and thus far the system has performed at expectations and beyond, meaning savings. It's gotten all of the incentives stackable with state incentives and local incentives. Utilities get involved. You have to understand that coefficient of performance allows you to reduce the grid demand. And in critical infrastructure that has no downtime, really, you really can help the utilities out with grid response, especially during peak times, by implementing one of these. And they will show you love for it in the form of support. That's been our experience here in the United States. Agawam High School is a 70-year-old high school that did some new builds. The reason I bring this up is in the third paragraph, you'll see 150 boreholes drilled to a depth of 500 feet. Originally, it was 250 boreholes to 300 feet, specifically because the contractors, this is public bid, it was bonded, so everything was open and public, the design as well. And I noticed that they were only going to 300 feet. I looked as a geologist, and there's a specific rock type that none of the contractors in the area had liked to drill because it required more money. Well, luckily we had the tools. We proposed a new design, saved hundreds of thousands of dollars in casing for the developer, but also reduced the space and the time. That can be done on campuses as well as educational, pharmaceutical, medical, health facilities, and so forth. So another way where a lot of this geothermal innovation has a commercial direct effect. All right, we have about 10 minutes left for some questions. Here's some contact information, but I truly hope you learned something, and if anything, that geothermal is pretty neat. But yeah, I really appreciate the opportunity. So Yoshi, back to you in the studio.
Thank you so much, Jonathan. Very interesting, and the abundance of experiences, the examples that you've showed us is just tremendous. It's very, very impressive. Lara, do we have questions from the audience today?
Yes. Can you
Yep.
look at the Q&A box? If you can't read it, I can read it to you.
Absolutely. So Anonymous writes, how does the cost compare? So sounds like an expensive, protracted process to obtain 4 megawatts of thermal energy. So 4 megawatts of thermal energy, if we're talking tonnage, it's close to about 1,000 tons of heating and cooling. So it's fairly large. The thing is, in new construction, the Division 23 mechanicals that were connected to that network for all of those buildings got the incentives that I mentioned earlier when I showed that green and blue box. That reduced their CapEx beyond the bore field and into the actual construction. So to show how the costs compare, if you were to compare that to air source heat pump, a system of the same size, let's just say something along the lines of $35 a square foot or something like that, and you were to compare that to that same system, because of the incentives, it would either be same or less. And you get those incentives as a direct cash payout after a full year of running, which is why the operation and monitoring is so important. So without the ITC here in the United States and that tax credit program, that was a barrier. I will totally admit that. But the bigger the so the bigger the incentive, the bigger the project, the bigger the incentives. That was what I was going to say. So we don't have the incentives in New Zealand. Okay, now sometimes the incentives may not be on capex, but they may be on tons and or tons of CO2 avoided. So if you were, let's say, doing end of life from fuel oil or gas to a geothermal system, that might be a way. It just depends. And I do know carbon credits are compulsory, but New Zealand happens to participate. And I know that from my old power gen days, but that might be something to look into for revenue streams to help offset the capex.
Right. Thank you. Well, there's a next question.
Yes. Okay. Great question. So 110 degrees in the summer. Yeah. So for example, the Southwest here in the United States, a lot of times evaporative coolers, water is a precious resource. And so you may get dinged for water usage by just trying to keep cool. What happens, for example, and I'll just use data centers as an example. Cooling just means removing heat, right? And so there's better ways to remove heat, whether it's adiabatic cooling, evaporative cooling, geothermal. What it does is, depending on your bedrock. So, for example, in the Southwest, you have a lot of sand, a lot of desert. You will have what's diffusivity, the inverse of the conductivity. It allows not to hold the heat, but allows you to get rid of it fast. And that will provide a way to get down to delta T that will make your cooling work a lot faster. So if it's overbalanced in the cooling, we see that a lot, actually. Excuse me. For facilities such as, just a quick example, lettuce refrigeration plants or ports, places like that, where you have cooling dominant loads. Hopefully you have the bedrock that can be adequate for it. And that is really also with water table as well. Cape Cod here on the East Coast, Long Island, there is no bedrock to be found in the first 2,000 feet. It's essentially a glacial sandbar. And you'll see this, I'm sure, along the Pacific as well. That tidal wave, that tidal flow that comes in and out washes away heat extremely efficiently. So you could get very efficient cooling, and geothermal cooling exists in the tropics. So the systems last in terms of the boreholes that are drilled and the pipes that are installed. It's high density polyethylene, essentially gas lines. These are about quarter-inch to half-inch thick. They last 75 to 100 to 100 years operation and maintenance, right? The grout will last about 100 years, and the casing will last far longer than that. When let's say the building is demolished or it's refurbished, a lot of times those same utility connections can be reused for a new building. What happens in terms of the systems then fail? We now see a drop in pressure in the manifold. We are pretty sure that the pipe is in the year 2100. The pipes have gone. Well, steel can be milled with a drill bit, and the grout, as well as the high density polyethylene and the water, can all be milled with a drill rig and filled with cement. And that's plugging and abandoning. That's what you would do in a typical oil and gas well. And that would be done likely here, but between Now in 2100, who knows what they'll come up with. So I will say one other thing. Once the system is installed and everything is below grade, your heat pumps today in 2026 will have some efficiency. In 2030 and 2040, when your end of life comes back, those efficiencies, I'm pretty sure, just because Moore's law, right? They will get more efficient. You now may be oversized. Oh no, you have too much energy abundance. That means now you can build. That means now you may have excess thermal energy to then provide on the thermal energy network to someone else for a fee. That happens throughout Scandinavia. Heat becomes a utility to be exchanged. So don't fret if all of a sudden you're overly efficient and you oversized. Now you have an asset. So
Okay,
great.
thank you. You got some time left. I've got a few questions myself. Jonathan,
Yes, sir.
when you say COP, the coefficient of performance, right? Do you include in the calculations the actual pump circulation power needed? Because when
That's
you have that many boreholes circuits, I think that's quite a significant amount of energy used to circulate the
that
water as well.
That is correct. And so one of the reasons we don't like to go beyond 850, you'll see that, is A, circulation friction within the pipe itself, because it is 850 down and 850 up, but also, of course, the head. Now, once the system is flushed, and for commissioning, we run that parasitic load. So we have a baseline as to, how many strokes per efficiency, that kind of thing. But yes, it's definitely calculated in.
Right. Okay. Thank you. And I've got just one more question. At the beginning of your presentation, you talked about, the open loop, the wells aren't really that feasible anymore. Um, in this part of the world, we have quite an abundance of groundwater, and
Mhm.
it seems that balancing out the costs of boring and utilizing open systems, open loop systems, we often wonder, would it be better sometimes in our case to use open systems instead of borehole or closed loop systems? Well, what would you say to that if we say, if we're able to use that system instead? As you said, this is not feasible anymore.
Yes, and thermodynamically, if you could run high density polyethylene closed loop on a lake bed, you get the best of both worlds. You're still closed loop, you're still pumping through a pipe, not submersible pumping in lake water. You're not drilling a borehole, you're laying down loop off of a spool in a lake bed. And they do this in horizontal loops in geothermal that people may be familiar with, but that's a much lower load regime in terms of how much, energy that you can provide off of those systems. But if you're able to be grandfathered in the United States or in areas where water is very abundant, high water table, then absolutely, I would say combine new technology reliability with old world know how. Because, like I mentioned earlier, bedrock is great to hold heat if you have an abundance of it. Water, especially in tropical areas in the South Pacific, is a great to remove heat because you may have too much of it.
Right. Okay. Well, thank you very much. I
Thank
think
you.
it's coming to an end of our webinar today. Um, to be honest, I'm quite let's say, surprised, flabbergasted that in the middle of Manhattan there are so many geothermal systems, fantastic systems in place. And yes, that's very impressive. Thank you very much.
Thank
So
you,
that brings
Yoshi.
us to the end of today's webinar. On behalf of IFHE, thank you to everyone who joined us and for the questions, of course. And we also like to extend a sincere thank you to Mazzetti for sponsoring today's webinar and supporting ongoing education in healthcare design and performance. So before we sign off, we're excited to invite you to IFHE's next webinar, Cut the Carbs program, Cut the Carbs Awards program. That will be presented by Troy Savage, Director of Strategic Projects and Innovation at Mazzetti. So we hope you will join us next month. Thank you again. And again, to Jonathan, great round of applause. Thank you very much, Jonathan. And yeah, and have a nice rest of the day to everyone this part of the world.
Happy Thursday, everyone, from Wednesday on my side. Thank you.
Right, Thursday. Thank you. Thank you, Jonathan.